Hi everyone, this is your video on algebraic proofs and it's your proof intro. So we always start with algebraic proofs so that you can get an idea of how to write a two-column proof and the structure of it using something that you're a little bit more familiar with, which is solving algebra equations. So that's what this video is going to be about. In this video, I'm just going to go over notes and some properties. In the next one, I'll do some practice proofs for you. As always, what's on the left side of the screen is what I would normally project for you in class, and what's on the right side of the screen is your notes. I am using Kami to take my notes, but you can open the document in with Google Docs, or you can definitely do your notes by hand. It's completely up to you. All right, so before we kind of jump into the real mathy stuff, I wanted to talk to you about why we write proofs and why it's such an important part of what we do in geometry. So geometry is built, the entire course and the entire idea of geometry is built on some very foundational ideas. So proofs are a way for us to build more complex ideas from what we call undefined terms and then simple rules or things that we just have accepted as true. So like a simple rule that we just accept as true without having to prove it is the segment addition postulate, right? When we added those parts and set it equal to the whole thing, right? We don't have to prove that that's true. We kind of know innately that it's true. But there are a lot of other rules in geometry that are a lot more complicated, and theorems that are a lot more complex, that we use things that we already know to prove that those rules work all the time. It gives us a way to organize our thought processes and support our math with reasons. So you've probably seen in your, oh dear, my annotation isn't, I don't have the ability to annotate on here. Whoops, sorry everybody, hold on. Maybe this will let me annotate now. Ah, there we go. My drawing tool was not there. So you've probably seen before in like a science class or maybe an English class, something called a T-chart, where you would write statements on the left, and then you would write your evidence on the right, right? And you would have to support it with quotes from the text or with data from an experiment or something like that. Okay, it's exactly the same thing in geometry, and it just allows us to organize our problem solving and our logical thought processes in an order, and like actually write them in order from one to however many steps that you need. Okay. Yeah, so like I said, it's very similar to writing a research paper or planning for a research paper or proving an argument, where you make a statement, you make a claim, and then you support your claim with evidence. It's the same idea, but we're using it for math. Okay. And what's great about proofs is that it allows us to create new rules that are always going to be true. So if you remember going back to when we were talking about the different types of reasoning, the inductive reasoning versus the deductive reasoning. Remember, the inductive reasoning is the patterns, right? Where you would look at data and you would look at a set of numbers or a set of letters or a set of pictures and try to figure out what the pattern was. Oftentimes, if you would gather new data, you would realize that your original pattern was wrong. Right? So what we use deductive reasoning for and what we use proofs for is it allows us to create these rules from patterns, right? And say that those are going to be true all the time. And what's cool is once you prove that something is true, you don't have to show that it's true again, right? Once we know that it works, then you can just use it to build other things, which is kind of cool. All right, so let's talk about some basic ideas here. So geometry is something that called an axiomatic system. Ooh, very fanciful. You won't ever be asked to memorize that term. I just wanted to tell it to you so that you knew what it was. Okay, what that means is it's a system with a logical structure built upon a few agreed upon assumptions. Okay, so those are the like fundamental rules that I talked about a couple of minutes ago. Okay, so we use three different what we call undefined terms. Oh, sorry here. In order to build all of our other definitions. Okay, so your three undefined terms are point, line, and plane. Okay, so those are three terms that no one will ever ask you to define. There's no way to define a point without saying it's a point in space or a location in space, right? So we essentially say those are undefined, right? And we build other terms from those terms, which you can kind of see already if you look on the right side. I gave you two different definitions there. Where I asked you to pick out the undefined terms, right? So this is the definition of array. Array is part of a line bounded by one endpoint and extending indefinitely in one direction, right? So it's the ones that look like this, right? So you can see the undefined terms here, right? We have line and point, right? We use those undefined terms to build a more complicated definition. Similar thing for an angle, right? Now that we have a definition for ray, we can use the definition, or we can use the word ray in other definitions, right? So that's what happened with the angle here. So an angle is a figure formed by two rays, which is not an undefined term, but once we have a definition, we can use that term in other definitions, right? So a figure formed by two rays with a common endpoint, right? So there's that term, that point term again, all right? So what we're doing with proofs is we're taking these very simple ideas and things that you've already learned about and things that you know in order to build things that are a little bit more complex and show that certain things work in figures that are a little bit more interesting looking and kind of weird looking, all right? So let's talk about some algebraic properties. You should already know these properties because you've used them in pre-algebra, in algebra. You know these properties, right? But I'm going to give them a specific name here so that way we can use them in proofs. Okay, so these are your four equality properties. Okay, there's the addition property of equality, the subtraction property of equality, the multiplication property of equality. Well, that's not how you spell multiplication. Multiplication property of equality, and the division property of equality. All of these properties essentially mean what you do to one side, you must do to the other side. Okay, it's like the fundamental rule in algebra. So the addition property of equality happens when you add the same number or term to both sides of an equation. So for example, if I have an equation that looks like this, 2x, oops, hold on, let me erase. I didn't write that correctly. So if I had something like this, 2x minus 4 equals 8. If I add 4 to both sides of my equation, then that is the addition property of equality, right? If I subtract the same number from both sides, that's the subtraction property. Multiplication property would be if I multiply the equation by both sides, or multiply the equation on both sides by the same number, and division is if you divide by the same number on both sides. So in my example up here, that would be like 2x equals 12, and I go divided by 2 on both sides. So that, since I'm doing that on both sides, that's the division property of equality, right? So hopefully, right, you know those and you know what they are. It's just now we're giving them a name, right? So here's a couple of other properties that show up a lot when we're doing algebra. Okay, one is called the distributive property, which I'm hoping you remember, right? It always looks like this, right? So it's the one where you have a number typically on the outside of parentheses, and then you take that and you multiply it through to both terms inside of the parentheses. So say you had something that looked like this, 4 times x plus 3 right? I would take my 4 and distribute it to both of those numbers. So you end up with 4x equals 12. Okay, that's the distributive property. These next two properties, the reflexive and the symmetric, we don't use very often. The reflexive property is that a number is equal to itself, right? So you can kind of think about like your reflection in a mirror, right? Like you're still you, you are equal to yourself. The symmetric property is when you take two sides of an equation and you flip them, right? So that's the symmetric property. Right, so if nothing else changes but you flipped the order, okay? Then there's another one called the transitive property, which you'll hear me call the middleman property. And you can almost think of it like a chain, okay? So what the transitive property does is if we know A equals B and B equals C, then essentially what the transitive property does is it says, okay, B is the thing that's in common for both of these. So I'm going to cut out the middleman and just say that A is equal to C, right? If you wrote all of those together, these first two together, it would be A equals B, which equals C, right? So I can just, if everything is equal, I can just cut out the middleman, cut out whatever's in the middle, and you just end up with A equals C, right? So that's what I mean when I say think of it like a chain. It's like a chain of things that are equal to each other. And you can extend it to more variables. So if we also had over here and C is equal to D, right? I could say A is equal to B is equal to C is equal to D, right? So I can then, I'm still cutting out the middleman, right? I can cut out the middleman and just end up with my values on the end. Okay, so that's the transitive property, right? And that's why you'll hear me call it the middleman property. Okay, let me clear off my screen here. And then we've got one more property that's used more than any other property really in like it's the one that translates the best from algebraic proofs to geometric proofs. Okay, so it's called the substitution property. Okay, and you'll hear me call it the plug-in property. Okay, because what the substitution property says is that you can, oh, whoops, sorry everybody, nope, once more, there we go. Okay, what the substitution property says is that you can substitute or plug in equal things for each other in an equation. Okay, so there's a couple of places that you will use it, or a couple of situations in which you will use the substitution property. Okay, the most common one is when you're simplifying something on one side of an equation, or if you're combining like terms. So I have a couple examples for you here. Okay, so the first example I gave you is if you have in an equation 10 divided by 2, right? And I know that that's equal to 5. So let me zoom in on this side a little bit. So what that means is that if you have this in an equation, 10 over 2x equals something, then that's the same as saying 5x equals something, right? So essentially what I did is I took these two things that are equal to each other. Since I knew that this was equal to 5, I plugged 5 in where 10 out of 2 used to be, okay? Similar idea when you're when you're simplifying something. So in that second example there, I have this equation, 9x plus 3x equals 24. Well, I know that 9 plus 3 is equal to 12. I know that that's equal to 12x. Right? So essentially what I'm doing is I'm saying 12x, right? I combine my like terms, 12x equals, oh, well, I wrote that incorrectly. 1 second. Sorry, this should be 24. Sorry about that. Some of y'all are probably watching the video and be like, Miss wrote that wrong, which I did. Sorry about it. So here we're writing this, right? So essentially what I did is that instead of writing 9x plus 3x, I wrote it as 12x instead. I plugged in 12x where 9x plus 3x used to be, right? So this is me simplifying one side, and that's the key, that you're simplifying on one side of an equation. Okay, when you are doing something to both sides of an equation, that's always these properties, the addition, subtraction, multiplication, and division. Okay, but here I was only adding on one side of the equal sign. So that's not the addition property because it doesn't happen to both sides. It's the substitution property because it's only happening to one side. I'm just simplifying on one side of an equal sign. Okay, and then my third example for you here is if you're given this information, I know that x is equal to 3, and I also know that x plus y is equal to 14. Well, I can't solve this second equation because there's two variables, but I can say, well, wherever I see an x, I'm going to plug in a 3 instead. So I'm going to put the 3 right there. So what you end up with is 3 plus y equals 14. Right? So I plugged in a 3 where the x used to be. Right? So like that's what I said. That's why you'll hear me call it the plug-in property. All right? So I want you guys to give something a try. Okay? So you have this equation right here. Okay, 4x plus 9 equals 18 minus 1/2 x. I want you to see if you can solve that equation for x, right? And then off to the side, write out what properties you used at each step, right? So number the steps and then write out which property you used. So I'm going to go ahead and pause my own video for a second so that I can solve that, and then we'll talk about the properties at each step together. All right, so I'll see you in just a second. All right, y'all, so I hope that you solved this the same way that I did. Whoops, 1 second, hold on. Oh dear, give me 1 second, everybody. This ended up getting erased, hold on. Okay, we're back. Sorry about the mishap there. So I'm hoping that you solved this equation similarly to the way that I did. So I started with my given equation, right? So there's no real, and I'm going to list my properties here. Okay, so here there's no property really for the first. So this is like equation number 1, equation number 2, equation number 3, and equation number 4. Okay, so there's no real reason for the first equation. It was just like what was given to me, right? It was my given equation, right? So then here, to get to step 2, I added 1/2 x to both sides, so that's the addition property. Okay, so in order to go from here to here, I used the addition property. Okay, to get to step 3, to get to the third equation, I used the subtraction property. Apologize for my handwriting here. So I use the subtraction property to get to step 3, or to get to equation 3, right? So from here to here, I use the subtraction property. And then to get to my last equation, my last step was I used the division property because I divided by the same number on both sides. Okay, so those are the properties that I used at each step. Now, the cool thing about doing a proof or writing a proof is that you don't actually have to show all of this work right here. 1, 2, like I could eliminate all that work and just go from this first equation to the second, to the third, to the fourth, the reason that you don't have to show the work is that instead of showing the work, you told us the reason for the work right here, here, and here when you wrote the property or the reason out that you were able to go from one line to the next, okay? And that's essentially what you're doing when you write a two-column proof, right? Which is pretty cool. So let me erase my screen here. Okay, so what we do with two-column proofs is we use them to organize our reasoning with steps on the left and reasons on the right. Okay, so essentially we're going to take what we just did, this solving, and we're just going to put it into a T-chart. All right, so we're going to look at this one together, which you can see on both sides of the screen. Let me zoom out over here just a little so we can see everything. All right, so here is our example, and we have this very, very fanciful, very long algebraic equation, and the goal at the end is to solve for x, okay? So notice, you can see on both sides of the screen that there's no work shown, right? There's no like, they didn't show this, like +1, +1. Oops, hold on. That does not look like a +1. Okay, so like that's not there. The reason it's not there is because the work is over here on the reasons side. Okay, so let's talk about this. First, the very first thing is you always, 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 no matter what, is you always start with whatever is given to you. Okay, it's like your starting point, okay? So they will always have a statement that's written like this. It says given, okay? That's your starting point, okay? So no matter what, your first statement is always, you can write it verbatim, exactly as they wrote it in the problem, and then your reason is given equation, okay? When you are writing a proof, they'll also give you what's called a prove statement, which is your ending point, okay? So here, you have your given, this is your starting point, and then you have your prove, which is your ending point. So essentially, they're giving you the beginning of the map and the end of the map, and you have to find the path that goes from start to end. Okay, that's your job when you're writing a proof, right? You have to figure out and fill in the middle part, essentially, okay? So the reasons are always a little bit difficult for people to grasp, okay? Because sometimes it can be hard to match the reasons to the correct statement and put them in the right order. So the question you want to ask yourself always when you're writing a proof, okay, is what changed from statement 1 to statement 2, right? What did I do to go from step 1 to step 2? That's always what your reason is for your result for step 2, okay? So if we're looking here, what I did or what they did in order to go from step 1 to step 2 is they added 1, which means that the reason for step 2, right, is the addition property, because that's how I got to step 2. Okay, the reason is always, the reason that you list with the statement is always how you got there. Okay, let me change my color here. Okay, your reason should be how you got to that statement. Okay, like what rule did you use? How did you know that you could write that next statement? Okay, so I'm doing this on both sides here, y'all. So just hold on one sec as I try to write here. Okay, so this one is the addition property. okay? Then if we look back and go and we're going, okay, so what did they do from step 2 to step 3? What's different? Okay, and what's different going from step 2 to step 3 is they multiplied the 3 through the parentheses, right? They multiplied it through. So going from step 2 to step 3, how did I know I was allowed to do that multiplication, right? They literally did this, right? So if you remember, right, that is the distributive property, okay? That's how I arrived at my newest statement, okay? Right? So it's not what you'll do next, right? So like some people for number 3 would write, well, I'm going to subtract next. So they would put subtraction property for number 3, but that's not right, okay? It's the reason that goes with the statement is always how you got there, not what you're going to do next, okay? How you got there, not what you're going to do next, okay? So I'm going to fill the rest of these in on the right-hand side. I'm going to fill the rest of these properties in on the right-hand side so that you all can have those, okay? And you can kind of follow what they're doing. So to go from step 3 to step 4, what changed was they subtracted 3x from both sides. So that means the next reason is the subtraction property. Okay, and the same thing happened going from step 4 to step 5. They subtracted 12 on both sides. Right? So that means, right, so here going from step 3 to step 4, we did minus 3x. Right, so in order to arrive at step 4, I used the subtraction property. Similar thing from step 4 to step 5, I subtracted 12. That's what's different. So in order to get to step 5, I use the subtraction property. Okay. In order to get from step 5 to step 6, they divided by 2. Right? So that's how I arrived at step 6. So that's the division property for step 6. And then all that happened for number 7 is they did a switcheroo, right? They switched the x and the negative 3. Okay, you may be thinking, well, why do I have to do that? Because at this step, I already have x equals something, so shouldn't I be able to stop right there? The problem is that in a proof, your last step must match the prove statement exactly. So since the prove statement in this problem, because the prove statement is x equals negative 3, then your last step must be x equals negative 3, exactly. Like you can't have it be out of order, okay? When you're writing a proof, and this is the one thing that I didn't talk about, that your information, okay, your reasons are always going to be one of these things. It'll be given, so the information was given to you. It will be a definition, so like the definition of complementary angles, for example, right? Or the definition of angle bisector, or the definition of midpoint, okay? It could be a property of a figure, or like a rule that you know about certain figures or lines or angles, or other theorems or other rules that we've already proven. So proven theorems. Okay. So all your reasons will always be something like that. And if you remember some of the videos from Unit 1, a lot of the times we took rules that we knew about geometry and we used them to write equations, right? We used the definitions in order to write equations. You will do a very similar thing when you're doing geometric proofs, right? You'll be given a scenario and then asked to solve for something. And the only difference between what you were doing originally and what you're doing now in a 2-column proof is that instead of showing the work, you just have to write out the reason for each statement. Okay, basically support your statement with some evidence. All right, so here's what I'm going to do. I would like you all to try this one right here on your own. Give that a try. Okay, and I'm going to pause my video so that way I can write out some of these reasons. So pause the video, try it on your own, and then check back in a second to see how you did. All right, y'all. So here is the solution or the reasons filled in for this algebraic proof. So I'm hoping that you got the given correct. So remember, the reason always for the first one is given, right? You always want to start with what is given to you. Okay. Now, what I'm hoping happened is that you got all of these in the correct order, but what might have happened is they may be shifted, like down or up one. Like you may have gotten them in the right order approximately, but maybe it's like shifted up or down one. So I want to make sure I explain the reasons to you about why each of these properties shows up for each step. Okay, so remember, the question you ask yourself is what changed going from step 1 to step 2? What's new? Okay, and what's new is this 10. And that 10 is being multiplied. So what I did is I did times 10 on both sides. Since I'm multiplying by the same number on both sides, that is the multiplication property, right? Times 10 allowed me to end up at step 2, so that's why multiplication is the reason for step 2. Okay. Now, you may, right, some people might have written division property right here on number 3, okay, which is not actually what's happening here. Okay, the reason this is not the division property, and you probably thought that because you went, oh, they did 10 divided by 2, right, and 10 divided by 5 in order to get 2 and 5 here. Okay, but you didn't divide by the same number on both sides. Unless you are dividing by the same number on both sides, it's not the division property. What actually happened here is you simplified. Okay, you simplified 10 divided by 2 and called it 5 instead. 10 divided by 5, you called it 2 instead, right? Because you're not doing the same thing to both sides. So remember, whenever you are simplifying something on one side of an equation, or maybe simplifying two different things on either side of an equation, that's the plug-in property, the substitution property. All right, so let's see. Let's take a look at, so going from 3 to 4, I want to ask myself what changed, and it looks like I did the distributive property. Okay, I took my 5 and I multiplied it through here, and I took my 2 and I multiplied it through, right? So I'm using the same property on both sides. So what allowed me to get to step 4, right, was the distributive property. Okay, that's how I arrived at step 4. So that's what the reason for step 4 is distributive property. Okay, then I have to go from step 4 to step 5. I want to look at what changed, what did I do, how did I arrive at step 5, right? And I arrived at step 5 by doing this, minus 2x. So I subtracted 2x. So that's how I arrived at step 5. So the reason for step 5 is subtraction. And notice I did the minus 2x on both sides, right, of the equal sign. That's why it's subtraction and not the substitution property. Okay, from 5 to 6, I added 15 to both sides, right? So I arrived at step 6 by doing addition. So that's why step 6 is my addition property. Okay, and then from step 6 to step 7, I divided by 3 on both sides. okay? Which is why that's how I arrived at step 7. So the reason for step 7 is the division property. What some people will do is they'll put symmetric down here somewhere because and you might have done that because in my previous example, the symmetric property was the last one. But remember, that only happens when you take an equation and you flip it, like you switch the order of what's on the left side of the equal sign and what's on the right side of the equal sign. So if you put symmetric property on here anywhere, you are incorrect. You didn't need to do that. All right, so those are all of your notes for algebraic proofs. The key thing to remember is where to put the reasons. Okay, it's always how did I get here, right? How did I get to this next step? Not where am I going to go next. It's how did I get there, okay? So I will see you all in the next video where I'm going to do a couple more practice problems with algebraic proofs for you. See you in the next one, everybody.